Now, unrelated, not directly related, at least to the first problem, gave you this picture that the vector v, negative 4, 7 means, or is identified in the plane with a vector that goes from the origin to the point negative 4, 7. So there's your vector v. This is a representation of this vector in the plane. This vector is a column vector. It's consisting of two integers in this case. In general, vectors that are represented in the plane, well, the set of vectors where you have two real numbers here could be represented by points in the plane. And any point in the plane has coordinates which are two real numbers. So if we had a point out here, it would be identified with a vector that we could sketch from here to here, and with the pair of coordinates we have here, say x1 and y1. Okay, so that's the identification of column vectors with ordered pairs with points in the plane. Now, you're given three vectors. One of them is 3, 2, that's a vector v1, so that's a vector 3, 2. Vector v2 down here is 3, negative 2, and I think I actually wrote this one down. It should be 2, 3. And then we have another vector v3, which is kind of labeled in an inconvenient place, so I'm going to kind of smudge that out. I'd say erase, but it's going to smudge. We'll put the v3 over here. And that's the vector 6, 10. Messing this all up, let me fix this a little bit. Okay, so kind of get rid of some of the smudginess up here. Let me draw this. Write this as a column vector 6, 10. Now, how do I know? Because this vector is pretty close in direction to this vector. How do I know that this vector, if represented in the plane, makes a steeper angle with the x-axis than this one does? How do I know this vector is going to be steeper than this one? Well, because the rise over the run, if we go out to the coordinate point, the rise over the run from the origin out to the associated point here, this point, is going to be 3 over 2, which is 1.5. And the rise over the run here is going to be 10 over 6, which is 1 2/3, close to 1.7. So this one is somewhat steeper than this one. And if you're trying to draw these and represent them, you want to think about such things. Okay, then you were asked to sketch a line through the origin parallel to the vector v1. Well, that vector is going to go right through the vector v1 as I've represented it here. It's got to be parallel to it, goes through the origin. Vector v1 starts at the origin, goes out to the point 2, 3. So there's the line. Okay, I know the u vector, the stuff in orange, hasn't been drawn at this point. Then we want a vector through the tip of v3 that's parallel to v2. Well, there's the direction of v2, so this line is supposed to be parallel to v2. I'm not sure I did a good job. Didn't do that badly, but there it is. Okay, now that would be the orange line and this white line. Then you're asked to draw a vector starting with its initial point at the origin that's 3 times as long as v1 and in the same direction. Well, if you're going in the direction of v1, you got to go along this line. And if it's 3 times as long, then it's going to be 1, 2, 3 times as long. Maybe it'll be out to here, maybe it'll be out to here. We're doing just a rough sketch, and I'm not sure I got this vector drawn quite to scale with this one, so there's no indication or no assumption here that I've drawn this well, but I've got at least a schematic that shows the relative positions of these vectors, shows these two lines and so forth. And now I'm asked to do a vector from the origin to the point of intersection. Well, that's this orange vector that I've labeled u. Okay, then a vector along the line that we drew here from the tip of this vector, from the intersection point to the tip. That's our vector W. So now we can say that the vector V3 is equal to the vector U plus the vector W, in the very clear sense that if U starts at the same point that V3 does, then we move along U until we get to a point that we can reach by moving along a vector parallel to V2. Okay, and we can reach the tip of this vector, so that if we go from this point to this point and then put this vector together head to tail with this one, we get to the end of this vector. Okay, so that's kind of the sense of vector addition. So now a question that I want to pose is, well, U is obviously some multiple of V1 and W is some multiple of V2. What multiple of the vector V1, the 2, 3 vector, would we add to what multiple of the 3, negative 2 vector in order to get the 6, 10 vector? Now, I digressed at that point to other questions because of the order in which the questions were done on the document, but now I'm going to go over here and answer that question. Okay, so I'm going to say, well, U is some multiple of V1. Let's let C1 be the multiple of V1. Okay, and that's V1, not a U or something. Okay, so we got U equals some multiple of V1, C1 being the factor. Okay, the multiple, the number we multiply by V1 to get U. And W equals some multiple of V2, and I'll use C2 for the number that we multiply by V2. Now, U plus W equals V3. Again, U plus W has to equal V3. Now we just write down what V1, V2, and V3 are. Here they are. So we got C1 times this plus C2 times the V2 equals the V3. Okay, then I ask, well, what do we do? What's the obvious thing that we can do to this? Start simplifying it. And somebody said, well, you add the two things. Well, we're gonna, but we don't want to add them just yet. We first have to multiply this one through by the C1 to get this, and it should be clear that if I multiply C1 by the vector 2, 3, I get 2C1, 3C1. And multiply the vector 3, negative 2 by C2, I get 3C2, negative 2C2. And that has to equal 6, 10. Now what have I got? Well, I've got two vectors here that I can add, so I get this. And that should be completely obvious. What can I do with this? Now, somebody said write down an augmented matrix. Well, you're skipping a step, but that's where we could be headed. The other thing is we could write this as a matrix equation. Well, let's first just write out what this literally means. This means that this equals 6 and this equals 10. So let's write that down. Well, now we're on pretty familiar ground. Now we don't have variables x and y. Our variables are C1 and C2, but we treat it exactly the same. We've got two simultaneous equations in the variables C1 and C2, the unknowns C1 and C2. We can write an augmented matrix, reduce it, and when we get down to the end, if it reduces where we have the identity on the left, then we can just read off our solution. C1 equals whatever, C2 equals whatever. Alternatively, we can write this as a matrix equation. Okay, the matrix equation excuse me, would be the matrix 2, 3, 3, negative 2, the coefficient matrix, multiplied by the column vector C1, C2 equals the vector, column vector 6, 10. So that C1, C2 is equal to the inverse matrix multiplied by the 6, 10 vector that I'll show you just briefly because I'm past the point at which this thing will balance. Okay. All this should be very familiar to us at this stage because all this just goes back to chapters 2 and 3. 1 and 2 actually. And chapter 3 talks about determinants. Where does that come in? Well, we don't bother trying to solve this or this if the determinant of this matrix is 0. If the determinant is 0, that means a matrix is singular. It means it won't reduce to the identity. It means you can't take the inverse. It means you can't solve this, and it also means that this matrix is not going to reduce to the identity, so you can't solve this either. Okay, well, we'll go on with some of these other questions.